Hello everyone, and welcome to the video talkthrough for From Social Science to Data Science by me, Bernie Hogan. This is Chapter 3, the data frame. So the learning goals for this one here today are to kind of get used to the idea of a data frame, what we'd want to do with it. Well, to think of it to store data in a row and column format, primarily. We're going to get data into that data frame from a list, from a dictionary, or from a series. We're going to get data back out of that data frame. We're going to do that again. See that by column, by row, and by single cell, and maybe some other ways as well. We're going to change the data frame in some ways. We're going to want to change it by adding a column. I'll show a little bit about adding a row or combining that as well, but we're not going to look at that too much today because that's going to be focused on in a subsequent chapter, Chapter 5, on merging and grouping. But nevertheless, we're going to want to introduce it just a little bit because that's really common in just about any data framework. We're going to want to understand how to use map, apply, and applymap. Now, in the last chapter on the series, we saw the use of map, and that was for each element in a series, and we'll see how that works over here with a data frame. And we're going to want to see how NumPy stores an array. We might want to ask, what's the difference between an array and a data frame, and when do you use one or the other? And so we'll just briefly touch upon that as well. And then, so we'll just distinguish those between the data frame. Okay, so let's get into it. So from a series to a data frame. So to recall what a series is an object in pandas that represents a single distribution with an index. And you can get data back out of that series. You can either do it by position, starting with the 0th position in Python, or you can do it with the index value itself. Sometimes the index will have a label, maybe Monday, Tuesday, Wednesday, and so forth. So that works like a list and like a dictionary, but it does it only for one column of data. Here we have an example. Here we have our, it's got the index, and this might be a float value, so 3.1214, whatever. Not a number, could be. And it will have the series can have a name as well. It doesn't have to have a name, but you can assign it one. Now, if you have multiple distributions that you can align in some way, then you can consolidate them as a data frame. And we usually align along the index. And by that I mean, let's say we have a second series, and it also has index 1 and index 2 and index 3. Then pandas can know that we're going to line them up so that the two index 1 values are right next to each other. The cool thing about it is that it doesn't, you don't need to have them sorted in the same order as long as you have the same index values. It kind of knows that, the Monday from this series should go with the Monday from that series. Okay, so because it includes multiple series, and each it's going to be its own column. Now, each column can have its own data type, and that does suggest or that the data frame has an implicit logic to it. So it's not just like a rectangle. We think about the columns as being variables or measurements, and measurements generally of a consistent type. And we think of the rows as representing cases. So one instance or something. It might be a user and the user's profile information or detail information. It could be a document and features of the document. But indeed, that sort of that row column structure really permeates the data frame, and the way we the reason why there would be some kinds of syntax that are simpler and easier, because we would want to query by column more regularly, and some syntax which is a little more tricky but more relevant for thinking about it in a different way. Okay, so if you imagine you have these different series, and so you can see here that each of the columns would have its own object type. We have a float, a string object maybe, and notice here I put in a list. You can actually have just about any object in Python in an element in a series. It's not just text, it's not just numbers, but depending on the object that you have in there, it might be easier or more difficult to work with in this format. But it is common to have a list or even a dictionary inside of a cell in a data frame. So now a data frame is, thus we can see it's like a table, and we commonly refer to row column data as tabular data. This is like in spreadsheet programs like LibreOffice Calc or Microsoft Excel, Google Sheets. So now with a data frame, we don't usually edit or manipulate the table directly in the way that we would with pointing or clicking or editing a cell. So imagine now I'm going to move over here to, this is Microsoft Excel and demo tables. So you can enter all this data here, of course, in Excel, and we can move it around like this, which is very simple to do. And you know, maybe it's a bit too simple there, and we 1966 or something, and that's not the right value. I have to remember to go undo. Now, this is not to give a slight to spreadsheets. I don't want spreadsheet people coming after me, but the thing is that spreadsheets can be really powerful, and I actually use them quite regularly in my work. Oftentimes, you'll want to put your data into a spreadsheet because it's faster to sort or faster to filter for very one-off sorts of work. If we think back to the first chapter on fixed costs and marginal costs, well, just about everything here is going to be a marginal cost. Every time we click, we have to remember which click and resort again. But it's still very useful for as an exploratory tool. But as a programming tool, this kind of falls short. You can program it with a VB script, and Python even can interact with Excel, which we'll see in the next chapter. But it still has this sort of anchoring on the data that's in front of you rather than what you want to do with the data. Okay, so one of the advantages of doing it in a data frame then, or it's like an abstract object, is that you might have really large tables that will be very unforgiving if you open in Excel or try to open in Google or Calc. And you may also be, like I said, they're tempted to move things around or shift things with pointing and clicking in a way that is hard to repeat or hard to maintain. One of the things that's nice about data frames is it also gives us some flexibility in how we store. With a spreadsheet, you're really thinking about it in terms of a rectangle. But we can have, say, multi-dimensional axes. We can have an axis where, like, one axis is the year, but then there's a sub-axis for months, or for different hierarchies, an axis for countries and a sub-axis for counties or sub-level divisions. So we can be more flexible with the data frame as well as use like much larger data. So each data frame as an object is going to have an index, and you can query that index, and it'll come back. It's like it should come back as like a list, and columns as well. And the columns, they'll be on the top. Normally you'd think of in a table, and they can come back as a list as well. And you can assign new names to either the index or the columns by sending a list of that shape back to the program. Okay, so we'll see that now in a sec, but first I want to talk about creating a data frame, just real simply, and then we're going to go into JupyterLab and then kind of run through some of this. So there's many ways to create a data frame, and in the next chapter we're going to see a lot where we just use a method like read CSV or read SQL, and then the data will come right in as a data frame. And depending on what sort of method we use, like read SQL, it might come in a really smart way, which will remember whether it's a data frame or a string or that, whereas read CSV is not so smart. I mean, not to slight the read CSV. Part of it is you can specify the data types, but otherwise it's just going to assume strings, and so depending on the data type, you may have to do more fiddling with that. But we want to start simple. We want to start not by like just using a method and getting data from elsewhere, but using the kind of the basic data types from Python and showing how you create a data frame there. So you can instantiate an empty data frame, just like so, and it's going to have no name, it's going to have no index, it's going to be of shape 0, 0. But so it's not very exciting. But you can also pass in other things. Here you can see what I've done is I passed in a list of lists. So that's going to look like a data frame if we go and look at it later. It'll just go A, B, C, D, E, F, X, Y, Z. It's kind of a table. And I didn't pass it an index, and I didn't pass it any column names, so it'll just be 0, 1, 2 on the side and 0, 1, 2 on the top, I guess because it's 3 by 3. Now for dictionaries, you wouldn't just pass the object the way you would a series or a list. Instead, you'd use the from dict method. From dictionary, and you can see here we have a dictionary, and the dictionary has like the name of the Muppet, and then we have the species, first appearance, and gender there, and you'll see that I have these columns down here. Maybe it's a bit hard to manage there, but here's what it looks like. And the idea is that when we have this dictionary, the keys are going to refer to like the index, and then the values are this list. Now I've set this up as a dictionary so that we have 3 entries in each one of them, so it's all really nice and tidy there. If you don't have it that way, then Python may throw an error, or it may add in some missing data, depending on the context. You'll also notice down here I've got some parameters like orient index. We'll see in JupyterLab what happens if we orient it in a different way. It'll end up with Kermit, Piggy, and Gonzo at the top, and so it'll be flipped over. I mean, it's still data, but it doesn't actually doesn't work for the logic that we want of the data, where we have variables in the columns, and then cases of them, such as the different Muppets in the rows. Okay, so let's go over and have a look at JupyterLab, and here we are. I'm using this notebook here. It's just all the code from the book. Once again, as usual, we're going to restart the kernel and clear all the outputs. Now with this one right here, it should be the case that I can run in different bits, because it's actually a pretty long workbook, and I'm not going to be able to cover all of it. But we're going to want to be mindful of what the Muppet DataFrame Muppet DF is. So we can see here. First, I'm going to load pandas as we had before, and now we can create a series like we've done before as well. Now let's have a look at that series right here. Okay, so now if I make it a data frame, it should just be pretty much the same thing, right? Well, it is kind of, but as we see here, it actually looks a little nicer. And in JupyterLab, it has this nice sort of HTML look to it, and it has a 0 up here. Why that? Well, because we never named this series, and so it doesn't know what column name to give it, so it just says 0. Now we can see here, if we give it a name as the series, that name then propagates over to the data frame. So let's have a look at that. Muppet type. There's the Muppet type there. And you can see here now, I mentioned columns, and if you can pass a list of the same dimension. In this case, there's only one column, so we pass that list, and it's going to be called example name change. And there we go, example name change. So there's a couple ways I'd like to show here to create a data frame. Generally, you don't want to keep adding to a data frame. You want to kind of structure whatever data you had already, and then just make a data frame once, or make it a limited number of times, and what we'll see later, concatenate them. So we're going to want to get good at taking things like lists and shaping lists around. Lists are pretty fast to use. Data frames are not so fast, but they're really flexible. So we try to create and destroy data frames as rarely as possible, and use things like lists as much as possible. So here's a Muppet list. It's a two-dimensional list. You can see a list of lists, as it were. And now when we create that data frame, show it, we're going to see it right here. Yeah, now we have like a table. And so it kind of has the same structure visually as it does down here. It might help you think about how the list of list is going to look in the table. You see here, and now I can add some column names afterwards. You can also pass columns as a parameter, or the columns parameter. You can pass this to it when you first instantiate a data frame. Here's a Jupyter tip if you haven't seen this before. And if you press Shift and Tab inside a method like this, if you're not sure what parameters it has, just see that right there. Have a look. So DataFrame, when it has our data, things we can have another parameter is called index and so forth. It kind of goes through all of the documentation right there, including even some examples. So there's a lot here to digest in the DataFrame lecture, but if you remember one thing, perhaps you can check this documentation right here at your fingertips, but it's got to be inside a parenthesis. So we see down here from dictionary method, which I'd mention next, put that tab there, and it has things like orient, whether onto columns or so forth. Okay, so you'll notice here what I've done is I've set the name of the columns, and the next thing is to set an index. So I set the index to be the name. I just notice what that means right here. So up until this point, we've had an index that's numerical, and so now instead I can set the column to it. Now you notice I also use the in-place equals true parameter. If I don't use that in-place equals true parameter, you'll, I guess here we'll have to roll back the tape a little bit and do that. Now if we just see it this way right here and it displays Muppet DF, we're not going to see a change to Muppet DF because it set the index to a series or to a data frame and returned it. So that we'd have to say like x equals, and then instead it would be display x. See, so like that. So in place equals true ensures that the change happens where you want it to happen. Okay. So you can do it from a dictionary as well, and for dictionaries it might wonder what the keys should be. Should the keys be the index? Should they be the columns? And the orient parameter helps us figure that out. So right here it says orient index, so the keys are going to be the index right there. And that tends to be what I would use generally, but it might depend on how the data comes down or is otherwise structured. There might be ways you want to orient it differently. But here we can see it orienting by index, and it works just fine. You'll also see I've put columns in here as well inside the from dict, so we don't add the columns afterwards. Let's check this out. Now we've got it all done in one little line there. Okay, so we can see here if we orient columns instead. You might have been curious about that. Kermit, Piggy, and Gonzo are in the columns there, and this doesn't really make a lot of sense because each column generally we care about its data type, whereas with the rows we think of them as cases. Now to kind of reinforce that here, looking down below, when we query to see what information should we get from the data frame, it's going to focus on the on the columns. So let's go back here. So several ways to describe a data frame. Well, I'm going to introduce them first, and then we'll go back to JupyterLab. The simplest is probably len. You know, the number of things in a data frame. But remember, in this case, it's the number of rows. Again, reinforcing that. Object.shape will return the dimensions, and it'll be rows and columns in this sort of these parentheses here. That's called a tuple. You can use info as well. That'll give it a little bit further. It'll list the columns and their data types and tell about memory footprints and stuff. And describe will give you some numerical descriptions, things like the mean or the median value. So if your columns don't have numbers in them, then it's not going to describe them. So yeah, let's pop back and have a look at that. Okay, so I just did them all in one go right here. So the first one, we can see the number of cases is len Muppet DF, so it's 3. And you'll see the shape of it. Again, 3, 3, so probably should have made one of them 4 just to make sure. Now for what it's worth, I don't think that, yes, that's a different data frame down here, which makes sense because we still have the columns being species, first appearance, and gender. And so this is the, as we can see here, this is the info statement. 96 bytes, I mean, it's not really a big data frame. And then describe down here. The only number that we had in these columns was first appearance. It was a year, ranging, I guess, from 1955 to 1974. So it's still, it puts these in this this output right here as floats, even if they were integers to begin with. So right now we can see pretty quickly that there's methods that allow you to explore your data at a glance. Depending on the sort of data that you have, this is going to be really relevant when you first load it in. Do you want to know how large the data set is or how many columns it has? I actually find, relative to these, that just also printing just like dot columns and reading the column names can be really helpful as well. What I don't find helpful, I always wanted to find helpful, but I always always been disappointed by, are there's like a lot of packages out there where it's like an add-on for Jupyter Lab. Often you'd have to install Node.js first or something else. And then you can see your data frame in a window. Maybe it's a rich text window, so you can like scroll around and zoom in, maybe even edit. But those they always to me tend to be like not as good as like a spreadsheet program, a dedicated spreadsheet program. So if you want to visually explore your data, just go to a spreadsheet program and kind of lean on the strengths of Python for the Python. Also, you can look at just a number of rows. So looking at the top first few rows would be with head. It'll give it the first 5. If you put a parameter in there, it'll give maybe the first 10 or 20 or whatever. Tail will take it from the bottom, and sample will just randomly sample from inside the data frame. So other than just getting data into a data frame, we might want to get that data back out, of course. So one of the ways that we do that is by using an indexer. Now in Python, we see indexers a lot, but we don't normally call them that. We just call them just like the brackets, I guess. So we have a list, and then we have the brackets, and then in the brackets would be the number 2, and then we say we get the second element out of the list. But those brackets refer to an indexer. And the thing is that you can have different indexers for the same object. We haven't really seen that yet, because like a list, you just have an indexer and it's a number, and a dictionary, you have an indexer and it's a key. And so it's the same thing with a dictionary. We store them in the curly braces to suggest that they're a set, or the keys, or they have keys. But we index them. We get the stuff back out by using the square brackets. It's generally the case in Python. Okay, so have a look here. If we want to get the column out, then we just use the brackets as they are. So if species, we get the frog, pig, and unknown. It's debated what Gonzo's species is. It weirdo, maybe. So you can also get the rows as well. And so you can either get the row by a label. So if you recall in our small little table there, Kermit was the index, and Miss Piggy and Gonzo. So if you use LOC, you'll then get a series representing that row. You can also do it by position as well. So it's the same thing. Kermit was in the first position in the table, and so iloc 0 will get you that. So I don't know. I try to remember that L means label, and so that we use that one with the labels and the other one with position. It's a bit tricky though. Now this is getting a series, but maybe you just want to get a single piece of information. Well, there's a number of different ways that you can do that. If you'll notice here, there's a number of different ways of doing that. If you'll notice here that these all return a series. So then I guess you could then, with each one of these series, then in this case you could put species after it, and then that'll get frog. So if you just want to get the thing in there. And similarly down here, this is a series. So you have this species, and then you could go species and Kermit. And so then you would get similarly the frog, or species and Miss Piggy, and then you'll get pig. But is there a better way to do it? Is there what we might say a more Pythonic way of doing it even? And that is indeed to use within the same indexer the row label and then the column label, and put a comma in between them. So for LOC, it's row label and column label, or for ILOC, it's row position or column position. And I'll show that here now. Okay. So we can see here, a single column, just like that. In this case, I used two. So I guess it was, oh yeah, it's Gonzo. And you notice actually also I didn't put in the slides, but you can retrieve multiple columns. But I want to highlight here and do that in JupyterLab. The indexer still only expects one thing, but that one thing can include multiple columns. So we cannot put two columns in here, I don't know, gender and what was the other one? Species and first appearance. There we go. That's gonna be an error because it only expects one thing inside the indexer, but that one thing can be a list, including the two column names. So like in this way, that's how you can get get multiple columns. Now to show the different elements here, or the ways of getting a single cell. One of the reasons I'm going to suggest using this syntax right here, other than how I describe it in the book, is that we can see it in terms of timing. So it's going to ask for Miss Piggy. It's a bit slow because I didn't set the number of iterations, and so it's running 100,000 each. I don't know if it's going to slow down the camera, or 10,000 in this case. But yeah, look at this. When we ask for it using the indexer where we have row and then column inside the same single indexer, it took five nanoseconds or 5 microseconds. And then if we do it this way, where we first get the series, and then for the series we take the key and then get the value, it's slower. And similarly, if we do the same thing but with the position rather than the label, it's still pretty slow. So there's actually like a real qualitative speed difference in using this particular syntax here. Do you know why? The others create an object in memory temporarily, a series, and so by having to hold that in memory and then look within it, it's just like taking up a little bit of resources. And so this way it zips on through. So another way to get data from a data frame is to slice. Now I did mention slice a little bit in the previous lecture on the series, but I didn't spend too much time on it. But here I did want to give a bit of a refresher. So to remember, we have a list here, and so let's say we want to slice it, so we only have from the first element onward. You'll notice if we have this colon here, and then if we put a 1 in front of it, we're going to say from the first one onwards. Now that's 0, 1, 2, 3, remember. Okay, and if we want to chop off the last one off the end, we can say go up to the last one. The list positions actually count both positively or forward and negatively. So you can put in, ask for this with 0 or 1, but you can also ask for it with -1, -2, -3. So if you go list -3, you can get that one. So the thing is right here, you can then chop off the last one, slicing it that way. So you can also then have this kind of middle here, where we can go from part of the range up to, but not including, this number right here. So we go, from here up to, but not including, and that's why, and that's so that if we went, say maybe 3 colon for the next one, they wouldn't overlap. That keeps the slices nice and tidy. So now imagine how we might do that with a data frame rather than just with a list. So if we did iloc colon 2, in this case right here, we're only going to get up to the first 2 entries. So we got Kermit Miss Piggy, but we didn't see Gonzo. There's more of that code in the worksheets, but I just wanted to cover that there, and you can explore the rest as you may. Masking, though, I think it's really useful to attend to. So With a series, what we would do is just give a boolean condition. Is it greater than 3, and then we like true, true, false, true. Well, with a data frame, you can do that too, but we do it on a per series basis. So we get one series, from the data frame, and then we ask the boolean condition of that. So if we had the first appearance of the Muppets and says whether it's greater than 1967, then we get like a false, a true, a true. Okay, so we got a new series, not a data frame. But then when we put that series back in, that like a mask, then we can use that to mask down our data frame. So similarly, like right here, and then it'll just show the Muppets where their first appearance was greater than 1967, like so. So a lot of masking, really really common in data frames, and it's common because you might have a really large data frame, and not all of the entries are relevant. Maybe you only want to look at entries from the root comment and not the other comments, or from, I don't know, all the posts in 2010, or that have mention a certain thing. These tend to all be done through these Boolean slices. It's also worth noting that the slices that return, they return a view and not necessarily a new data frame. But we'll cover that again later with deep versus shallow copies. So you can change the column in a data frame by adding a column of data, or you can change the data by adding a column. So here we have a very simple data frame from this dictionary. So it's just got Kermit Frog, Piggy Pig, Gonzo, and whatever. So it's just one column. It says species, and it looks like so. All right, so now if we want to add a column to this data frame, for example, we have a new dictionary right here. Now you'll notice that the order of the things going in the dictionary is different, but they still have the same keys. They still have a key for Gonzo, a key for Kermit, and a key for Miss Piggy. So when we make that a series called Muppet Year, we can then apply that series, or just add that series to our data frame, and then so it'll just be the next column over. But we can do other things in order to add a new column to a data frame. So for example here, imagine we want first decade. So first decade, we can use a little simple formula, like remainder division or long division. So imagine if you divide something by 10, if you divide 13 by 10, you get 1.3. But if you do it in an integer division where you have a remainder, you'll actually get 1 with a remainder of 3. So when is the remainder going to be 0? The remainder is going to be 0 when, on the decade. So we do that. We divide by the decade, times by 10, and now we got our first decade assigned to a new column, like so. So actually, it's pretty easy to add columns, and that's quite deliberate for a data frame, because there's lots of times when you're going to want to take columns and kind of calculate things with them, not just like the first decade, but maybe something a little more interesting. And so that syntax tends to be quite tidy. Adding a row in a data frame, on the other hand, is not normally recommended, and it's a bit confusing because, well, if you have different columns, they might have different data types, and so you'd have to pass a new object, either a list or a series, with all these different data types. And it doesn't really like, mapping by the column in the way that you would map by the index. So we don't normally do it, but you certainly can do it by going, your dataframe.loc, and then giving it a new index, not a new position, just a new index. It's like a dictionary like that, and then adding a new row to it. But we don't really want to do that. I don't really recommend it. Normally, what you would like to do is just find a way to create a data frame only once, or create it as few times as possible. Add columns as you need to, but if you're creating multiple data frames, you want to concatenate them rather than kind of add new data one at a time. We should be able to find a programmatic way to change different features of or different elements of the data frame, and sure enough, so like in the series we had a map, so you could map on either values from a dictionary, or you could map on some formula. So you could say, make it all uppercase or lowercase, or that sarcastic meme case online, in a map. But now a data frame you want to care about the columns and the cells, and maybe the any given column at a time. So map works the same way. Map means the same thing, really. You would use map to work with a series. So you often do that in a data frame to transform one column into another, or extract something from one. We'll see it later, for example, with a column of posts in a forum, and they'll have like bits of HTML in there for like, you should check out this link. So we'll be able to strip that out and then make another column with the text, but without the HTML, and we're going to use map to do that. So apply works on a per series basis. So instead of just like you take a series and you go each element, you give it the data frame, and it will, for each series, it'll do some calculation. Like you might apply min, and then what it will do is for each series, it'll give you the minimum value, so the minimum value for that column. It will give you, if you have a really long list, but it has 4 columns, when you apply min, you'll get a new series back that's got 4 elements, one for the min for each of the columns. Now, apply map is when you want to do something to every element in the data frame. So you're going across all the columns and then going within them and doing something to each element. And we can see this in the Jupyter Lab in a notebook where I have some movie ratings, and so you might want the average rating per movie. So this would be apply, and so we would each movie is going to be a column, and each user who's giving the movie ratings is going to be a row. So apply will give us an average for each of the movies. We might want to transform the column and round up or down or something, and I'll show how to change the whole data frame so it's on a different scale. Maybe so we can compare the movie ratings to like a Metacritic score. So now you can chain these operations together and do all kinds of neat things with it, but we're just going to start from here. And so this is all the changing data stuff I showed in the slides, but yeah, you can check out the extra things here. Now this is kind of cool. I use here in order to create a data frame. What I've done is I've typed out what's like a CSV, comma separated values, but we didn't save it as a file and read that file. Instead, I've made it the string. For the string, it looks like a CSV. If I can zoom in here maybe a little more, and you see it's user 1 and so forth, and it looks like it's going to be a table. So I use the string IO operation, and then I put the this text inside that, and it's going to make it seem like even though it's a string, it's just like a file that we can use. So when I do that, we create a data frame. Let's check this out. And so these are not real movie names. These are terrible movie names I conveniently came up with a few years ago, and I guess I've stuck with since then. So here we have 4 movies, and we have 4 users. So if we want to, say for example, use apply, use the min. I'm going to skip a map for a second. We can see here the min for each one of them, which we've applied, like so. Now using map, we can make some changes here. So we see here lambda x divided by 5 times 10. What would that, or times 100? That's actually going to transform these movie ratings, which here seem to be out of 5, and transform them into something that's out of 100. So maybe we can compare them to Rotten Tomatoes or Rotten Tomatoes or Metacritic. Up here, we can see we've got our different movies, but now these girls is 1 over here. So what lambda's done is it's changed each one of these scores to be a score out of 100. 2.5 becomes 50. 1 out of 5 becomes 20. So it did it for the one series right here, and that tends to be how we do that in a data frame. Now you'll notice here some other things. We've done min, and min is a function, and in the last chapter we talked about functions versus methods. Now mean, we mentioned, is a method, not a function. So we can't just put apply mean in there. We have to do lambda score and then score.mean. So just watch that. And so now we get the average score across the users for each of these movies right here. And so you can see how you can kind of add and slice these up with apply and map going on. And you notice up here where I transform this one movie's scores into 100. Imagine let's do that for the entire table, and that will be using apply map. Okay, so I'll leave some of the rest of that for you there. Okay, so I want to just look here at the concept of deep versus shallow copies of things. Data frames, unlike a series, don't create a new instance in memory when we do masking. When we mask a series, we can actually return a new series, or a series that if we edit, it's not going to affect the previous one. But in this case, if we went Muppet DF and then we did some sort of mask, say mask it down to those over that were where the first appearance was after 1967. If we do that, that data frame we get back is actually a view to the old data frame. And so we might make some accidents if we try to change one and expect to be the other one to not be changed. We can avoid that by doing .copy. And here I'm going to actually just skip right on over to Jupyter and show that down here. So I'm going to reinitialize the data frame. We've got a new data frame here. Same thing, Kermit, Gonzo, species, appearance, gender, And so look at what happens here when we try to change Gonzo's species to a whatever from an unknown. It's going to say a value is trying to be set on a copy of a slice. Still, it's not the easiest, but the point is that we're trying to set on a copy of a slice. So this right here, this loc is going to give us Gonzo. It's going to give us this row as an object. That's its own slice. It's a filter, a boolean slice. And then from that slice, then we try to change the whatever value. But in this case, we really wanted to change it not in a new slice. We want to change it in the original data frame. So you'll notice then when we print the data frame, it didn't work. But now if we do this here by going right into the cell, that will succeed. So here's an example here about how a change might propagate. So we say we'll give our Muppet DF a new name. We'll edit the Muppet name in this new Muppet DF, and we'll see that change. Indeed, you can look in the original Muppet DF, and Kermit's species will be changed to lizard from frog. I'm pretty sure he's still a frog. Okay, so next I'd like to just have a brief mention of NumPy and NumPy arrays. Now we don't use them that often in the book here, but they are really useful. And under the hood, and the more computational you get, the more likely you are going to see NumPy and NumPy arrays. Now they're more efficient than a data frame, and they're stored differently. So they're more useful for linear algebra. You might say, well, why don't we use them all the time? Well, the way that they're stored differently is that they're only stored by position. And so querying from a NumPy array is not a very pleasant experience. You may find it easy to get a column, but getting a row is really, really tricky. On the other hand, because they're really fast, they can be used very effectively for a lot of linear algebra calculations. So you can set them using a collection, just any collection, and it'll just take the position and make an array. So an array object here would be NP array with 1, 2, 3, this list in there. And so now we have, this will just be an array with the numbers 1, 2, and 3. There's no index that you add there or anything. So it's common to want data sometimes of some dimension. Sometimes, for example, a table of random numbers. And you might want a table of random numbers. That's like you have 5 columns of random numbers and 1,000 rows. So you can take a range, an array range method, and get it to return, what was that, 5 times 1,000, get it to return 5,000 random values, and then have it reshaped into a nice tabular array of 5 by 10. So here's an example. Here we can just get not a range of random numbers, but actually the first 12 numbers, and then reshape them into some squares. So we'll see here how it does the rows, then the columns, then the outer columns. So if you run that, you'll see something that looks like this. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. Remember, we start from 0, so the A range 12 will get us 0 up to, but not including 12. So now, arrays are not really prevalent in the book, but you will see them in some places. In the chapter on NLP, they are used because there's arrays where the rows are going to be documents and the columns are going to be words. So it sets that up. It counts which words show in which document. And then through some matrix math, which really is in many ways kind of buried behind a couple of functions, it produces a new array that can help us see which words are the most distinctive or the most common, or give the most information. We also see in the network analysis chapter, because you can have an array. It's very common to see this as an adjacency matrix of the rows being people and the columns being the same people. So it's a friendship from one person to another person, or a reply from one person's content to another person's content. And so we see those in arrays as well. But for the most part, otherwise, I tend to focus on data frames because they are, I think, more suited to the tasks that I tend to do, at least prior to any sort of like large machine learning or classification work. So to summarize, tabular data has rows and columns, and in Python we generally use the data frame. We can also use the array. The array is only indexed by position. It's very useful for being really fast, but it's not so easy to get data out. By contrast, a data frame, as we see, there's many ways that you can get data. You can get it by row or column. You can get a single cell. You can slice, and you can also use like boolean filters to sort of winnow your data down a little bit. You can transform the data in a data frame. You can either do that for any given cell just by assigning a new value, df.loc, whatever, and then give it a new value. Or you can go and assign every value in a series, or for one column. You can make a new row, or you can transform the entire data frame itself. For example, using applymap. So sometimes a data frame returns a view of itself rather than a copy. Sometimes it returns a copy rather than the thing that you wanted. Be careful with these sorts of errors because you want to make sure that you're only changing the data you want. There's not really a lot of exciting questions actually at this one, which is, I guess, a bit unfortunate, but it's just part of the nature of the task. This is a tool as a data frame, and so when we actually get data in it, then that's going to be a lot more, there's going to be a lot more that we can do with it. But for now, actually, I still think it's useful to practice the basics and take these little tiny tables that I've done. I mean, I use the Muppets. It's kind of silly, but it hopefully it kind of suggests it being a bit tame rather than us sort of loading in, every title of every movie on IMDb with a million columns just to prove a point. That's very interesting to work with, but to practice, the language is quite useful with small data frames of 3 or 4 rows or 4 columns. As I said in chapter 1, I mean, maybe a computer scientist only can count to 0, 1, and n. And so if we can do it for n elements, try hand editing a small thing of 3, 4, or 5 by 3 or 4 or 5, and then get used to it, because then you can use the same code for much larger data when you go out and seek that data out in the world. So you can practice querying that data as well as creating that data. Find a specific row by name. I found it really useful myself to just say, look at a data set and go, like Gonzo's species. Now, how am I going to get that? And then just and kind of fiddling around and getting used to the code so that I go, okay, yes, that's how I can query that. And that it's very comfortable for me to kind of get used to those little basic operations before going on to the more complicated stuff. So I mean, they are more interesting when we add new data, and that is up next. So thank you for your time, and that concludes chapter 3 on the data frame. Up next is going to be chapter 4 on file types. But that's it for now.